I get around to it this afternoon, or if not this afternoon, tonight, I'll put up a practice task. And the practice task is the test for this class last fall. So, get a good idea of what the expectations are in terms of how long it should take, what kind of problems it's going to be, all of that. And what I would suggest is that, you go ahead and, maybe do all the problems, homework problems first, and then when you're going to take the practice task, set up just like you're going to take the test. Take 50 minutes, set aside, no distractions. Just try to go through it. Because I think what you're going to find, probably on the first test, you're going, holy cow, this is a whole lot longer than I thought it was going to be. And it's because you're going to be working through all the problems, and time's going to be up, and you're going to look. There's still 2 more pages to go. So I would use the practice task to really try to figure out, how long it's going to take you to do the test. So, I would try to take it just like a real test and see how close you get. And, on your test, it's going to be just like the quiz. You get a calculator, any calculator you want, and you get a pencil. So, don't have your book open doing the practice test, because that gives you a, sort of a false sense of, oh yeah, I know how to do this. So, I would really try to teach, treat it as much like a test as you can. Get in your room, close the door, sit down for 50 minutes, and see how you do. And what I'm going to do is, and again, depends on how you like to study. I will post the test, and I'll also post the answers for the practice test. I tried doing the test before I looked at the answers, just to see how you do. I mean, because again, if you open the one that's got the answers on, you're going, oh yeah, gosh, that's easy. I know how to do that. But so the goal is to use that practice test to try to figure out, this is what test's going to be like. This is how long it's going to be. I pretty much guarantee you're going to be surprised. It's going to be longer than what you would have thought if you haven't practiced. So I think it'd be really, really good to do the practice test and kind of figure out what kind of pace you need to work at. Okay? All right. And I was telling somebody else, there'll probably be a quiz next Wednesday, because I'm hoping if I can stay on schedule, we'll finish chapter 14. Monday, we'll have a quiz Wednesday morning, at the beginning of class. And then the rest of Wednesday, we can use to maybe do problems, in preparation for the test and stuff. If I don't get behind, that will be the schedule. All right. So, in order to stay on schedule, today we're going to talk some more about kinetics. And if you remember, the overall sort of idea about kinetics is thermodynamics tells us whether or not a reaction will happen. Kinetics tells us how fast the reaction is going to happen. We were going through this example of if I put bromine in formic acid, that if I can just kind of track the color change, that gives me a good idea of how much bromine is there. The other thing that can be very useful from that is that, if you have the reaction, if I know how fast one of the components is being used up, or one of the components is being formed, I should be able to get the rate for the rest of those components as well, right? And the way we think about that, and if we look at problem 14.8, if this comes up. Yeah, okay. So, in this particular case, what we're interested in is writing the rate expressions if I have these reactions in terms of, and as we said the other day, there's 2 ways you can be able to describe the rate. It can be how fast are the reactants going away, or how fast are the products building up. If I know one, I should be able to do the rest. And if we give this, first one where we have, 2 hydrogens plus an oxygen going to 2 waters, I should be able to describe the rate in terms of any one of those components. And if I think about it a little bit, the rate for this guy should just be equal to, and we always want to come back and we normalize to what it would be if the coefficient out in front is 1, right? So, if I look at that, I'd say that the hydrogen gets used up. If I take 1/2, because I've got 2 moles of hydrogen being used per reaction, so I'm going to look at 1/2 the rate of how the hydrogen is being used up, and that's just going to be the change in the hydrogen concentration divided by the change in time. Right? In its simplest form, that can explain to me how fast that reaction's going on. And again, that looks really easy. In reality, that may be really hard. I may have a hard time determining how fast the hydrogen is being used up. But just conceptually, if I know how fast the hydrogen is going away, I know how fast this reaction's happening. Now, the other thing, if, for instance, in the example that we were talking about bromine, if in this case it was a whole lot easier to measure the oxygen, I could also say that that's equal to how fast the oxygen is being used up. So that's for the minus sign. I use 1 mole of oxygen per reaction. So it's the change in the oxygen concentration divided by the change in time. So that should, again, describe the rate for me, because I'm using up 1 mole of oxygen for every 2 moles of hydrogen. But on the other hand, if it was easier to measure how much hydrogen was showing, or how much water was showing up, you know, if I was doing spectroscopy and I could see that hydrogen band, or the water band, I'd say, okay, I can also measure how much water is being formed, and so that would be the amount of water. And again, I get 2 moles per mole of oxygen, so 1/2. It'd be the change in water concentration per change in time. So depending on, you know, the techniques I have available, I may describe the rate in any one of these, but if I can do it for one, I should be able to then predict what the rate is for any of the elements. All I got to do is have the balanced equation and look at reactants versus product. And so the next one's going to be the same way, right? You know, if I looked at this, it'd be 1/4 the change in ammonia concentration per time, minus 1/5 the oxygen concentration change per time, plus 1/4 NO, plus 1/6 water. Okay, so you just, you know, the main point of this is that if the equation is balanced, you know, without a doubt, if I know one, I should be able to give you what the rates are for everything else, if you just take care of the coefficient. Right? Everybody's okay with this? I mean, there's nothing magic there. I just want to make sure that we understood that. Okay. Let's do this. Okay, so if we go back then to our bromine example, you know, so we got all these nice, you know, beakers down at the bottom. If we really wanted to see how the experiment was done, you know, what we would do is that, you know, in a spectrometer, we would look at where the bromine absorption coefficient, or where the bromine absorption line is, and it ends up it's about 400 nanometers or 398 nanometers. We would measure how much, you know, the intensity of this peak. The intensity of that peak is going to be proportional to the amount of bromine in solution, because the more bromine, the darker, the more absorbance there is, because we're plotting absorption versus wavelength. So higher absorption means more bromine. And so in order to try to get what the rate of bromine loss is, we just look at how the absorption goes down. And so, you know, at time 1, which would be at the beginning of the experiment, the absorption is really high. At time 2, you know, it's gotten lighter. The absorption is, you know, gone down quite a bit. And by T3, even though visibly, just looking at it, you may say, gosh, all the bromine's gone. You know, in reality, there's still some there. And the ratio of these peaks then will give us what the rate is, you know, based on how fast it's going away. So, you know, this would just be an example of, okay, if I looked at this experiment and I wanted to figure out, you know, what would be the easiest way to measure the rate of the reaction. Certainly measuring the bromine concentration, if I've got a spectrometer, would be a pretty good way to do it. What would be another way? You know, if you looked at this equation, what might be another way that you would be able to measure the rate then? Anybody have any ideas?
Formation product.
Okay, but which product? Which would be the right one to do?
Since it's forming H+, you could
Measure the pH, right? So, you know, if we measured the pH as a function of time, you know, the H+ concentration is going up. We ought to be able to use that as an indicator too. So if I've got a spectrometer, maybe I measure bromine, I got a pH meter, maybe I measure H+ concentration. It doesn't matter, as long as, you know, and typically what you'll do is pick the easiest way you can measure it.
Like you're making CO2 gas, so in the reading there was the pressure.
Yep. So you can put a manometer on it and measure how much CO2 you're forming. You know, if you know the temperature, you would know the volume of CO2. So there'd be multiple ways you could do it. And you know, the whole point is pick the one you have the right piece of equipment for, or the one that maybe gives you the best accuracy. But if you know one, you know them all. All right. So, you know, so what happens is that, you know, typically when we're going to have a problem that we're going to work, you know, we're going to get data like this. You know, and so, you know, we know now how we might measure the concentrations and all that's good, but in reality, you know, in class we don't have those tools, so you know, I'll be giving you data. In the format that you're typically going to get the data in is that, okay, if this is, you know, the concentration, or this is the reaction, you know, I look at particular times, I would give you the bromine concentration at that particular time, and I would give you what the rate is at that time too. And you remember the rates are always going to be in molarity per second. So the thing that we want to keep track of, and it's not always obvious, is that when we give you these rates, these are actually instantaneous rates. So, you know, at a specific time, if the concentration of bromine is this much in this solution, you know, this is what the rate is going to be. And that rate then, you know, since if we know the rate, you know, overall we can say that's how much bromine and formic acid is being used up, that's how much bromide, hydrogen, and CO2 are being produced. So, you know, in the end, typically it's going to be pretty hard to measure those instantaneous rates. So what we do is we end up, just practically, we measure average rates. And the way that we do the average rates is that, at a given time, time zero, the rate is this amount. At 50 seconds, when the bromine concentration is this amount, the rate and the instantaneous rate is this. In order to find an average rate, what we do is just take the change in concentration. Because remember, if we go back, the equation is just the change in concentration over bromine versus the amount of time that took to happen. So if we look down here, the two concentrations are 0.010, 0.020. It's in 50 seconds. So the average rate is 3.8 times 10 to the minus fifth molarity per second. So you might say, okay, that's pretty easy. But what happens then during the next 50 seconds? During the next 50 seconds, the rate's going to have to go down, right? Because the amount of bromine we have is less. And if we think about it, we said the rate is the change in bromine concentration versus the change in time. So if the bromine concentration is less, the rate's going to have to be less. And so if we just go back, we figure out again, we take the concentration at time 2, concentration at time 1 in this case. Now it's 100 seconds. So the rate's gone from 3.8 to 3.54, depending on when I actually took the measurement. If I took it at 50 seconds or I took it at 100 seconds. So, practically, this is the measurement we would normally make because it's hard to make those instantaneous ones. But in reality, this might not be so useful because the rate's changing every time. It's changing in between when I took it and when the next time that I can get the actual rate. So, this is it. This is the way we really make the measurement. What we really probably find more useful is the instantaneous rate. And what we're going to go through in a little bit, we're going to show we can actually get to a rate expression so that the only thing that matters is concentration. That's really where we want to end up with. Because then if I know the concentration, I can always predict what the rate's going to be. But and this is more for, hopefully conceptually this would make more sense if we think about it a little bit. So, for this particular reaction, and it ends up, we're going to show that it's first order. But if we look at, the concentration of bromine should go down as a function of time, right? We're using up bromine, it's going to bromide ion, and eventually it's going to asymptotically, approach a very low concentration of bromine. In reality, the bromine will probably never completely go away because there's always that one left. But it's going to asymptotically approach zero. So, conceptually think about the concentration of bromine going down with time. The other thing, though, that we want to, it ends up is probably going to be more useful to us, is that the rate is also going down as the concentration of bromine, right? Because the rate is the change in bromine concentration with time. Well, if there's no bromine, the rate has to be zero. So if the bromine ever actually goes away, the rate will go to zero, and it better be, that they both cross the intercept. That the concentration at zero bromine concentration, the rate better be zero as well, because there's no bromine left to react. So, this is just kind of to give you a feel for that. Because a lot of times you'll see this plotted both ways, and it might be a little confusing. Well, gosh, I thought that the bromine would just slowly go away. Well, the bromine slowly goes away, but the rate does follow linearly since it's first order with the amount of bromine that's there. Okay, so, so what we normally then would have is that, we would take and calculate these, average rates that we would have because, we can get the concentration and the rate at one time, concentration rate at the other time, calculate an average. As I said, the instantaneous rate is really what we want to know because that's going to be at a given concentration. This is what the rate's happening. And the way we do that then is that if you plot the curve, you can find the tangent to that curve at any one point. And so for a particular concentration or time, if we plot the tangent to the curve of the average rates, we can pull out what the rate is, at that particular time. So at 200 seconds, we can get that the rate's 2 times 10 to the minus 5 molarity per second. So once we get this curve, we know what the rate is at any concentration, and we know what the rate is at any time, as long as we know that it's a first order reaction. So the instantaneous rate is the more useful one, because normally you're going to say, gosh, if I have this much, what would the rate be? The problem is that we normally are going to collect the data as an average rate and then come back and determine the instantaneous rate by plotting.
No. I'll put it on public.
Okay. So, the other issue though is, and this is where it gets confusing sometimes, and so, it makes sense to speak up, and we'll go through this. But, if you guys remember, so when we showed the rates, we said, okay, the rate's equal to the change in concentration for bromine divided by the change in time. If all we're going to do is just say, yeah, okay, that is the rate, we define it that way, that's fine. But at some point what we want to be able to describe is the rate law. And the rate law is what's going to be what we're after and what's interesting to us. Because when we get to the rate law, at a given temperature, and we have to be careful about this because the rates are only for a specific temperature. So you'll always, later on in the chapter we're going to be able to be smart enough that we can say, gosh, if we know the rate at one temperature, we can calculate it at another temperature. But when we talk about measuring the rate, we're going to do it at a specific temperature. But this is really what we want. Rate equals a rate constant times the concentration of BR2. So how do we get to this? Because if you remember now, up until now we've always been talking about the rate is the change in concentration divided by the change in time. But if I really want to be useful, I just want to know what's the rate going to be when I put in a certain amount, in this case bromine. So we need to know what K is, and we need to be able to get the rate for bromine. But the other part that's not so obvious, and we're going to go through some examples, is that depending on the kind of reaction it is and what the mechanism is for the reaction, this may or may not be raised to the first power. If you guys have seen this before, this will make sense, but it could be that if it's what we call a bimolecular reaction, where one bromine molecule has to hit another bromine molecule, it may be that it's the concentration squared. If it's a unimolecular mechanism where bromine's just falling apart, then it doesn't matter how many other ones are around. It's just what's the concentration. But so to determine what the coefficient is on the bromine we're going to have to do that experimentally. You can't look at the reaction and know that this is going to be first order in bromine. And so what we are going to show over the next, sort of 15 or 20 minutes, we're going to talk about how to actually use the experimental data to find out what these coefficients are. In this particular case, we want to say, okay, how is the rate affected by the concentration of bromine? The way we do it is, if we look at the data that I've given you, we look at, okay, if I look at the rate for the bromine being used up, and I do it at 50 seconds and at 250 seconds, if I just take this rate divided by this rate, but then I also want to look at, the concentration at the 50-second point and the concentration at the 250-second point. So if I take the concentration, this divided by this, it's about 2. So as the concentration changes by a factor of 2, if I take the rates, this rate divided by this rate, the rate changes by about a factor of 2 as well. So what it's telling me is that it's proportional, and it's raised to the first power. If the concentration changes by 2, the rate's going to change by 2. If the concentration changes by 4, the rate's going to change by 4. I don't know that just by looking at this equation, because the equation doesn't tell me anything about the mechanism that's going on. So, what this tells me is that, I now know that the rate's proportional to the concentration of Br2, and so the rate then is just going to be equal to some constant, which we're going to determine experimentally, times the concentration of Br2. And the way we get that constant, and we'll do a couple of these examples, is, I know the rate, I know the concentration of Br2. Here, I can just solve for K. So, once I get to this point, I solve for K, and then I've got the rate expression, and from there on, at this temperature, I can always tell what the rate's going to be if all I know is the Br2 concentration. Okay? So, if it's a gas, pressure is going to be important as well. For this one, since it's in a liquid, pressure really doesn't affect things very much. So we really don't worry. So it's at a standard set of conditions. Normally, we're going to assume pressure is 1 atmosphere. Okay? But if we were doing it in a gas phase, and we'll show some examples of gas phase reaction, then certainly the pressure is important because the pressure is going to change the concentration too. Right? So, when we start thinking about gases, the concentration is directly proportional to the pressure. All right. Everybody okay with this? Yes, ma'am. So what we're going to find is in this example, it ends up, it doesn't matter how much formic acid I have in this reaction. That if I put these guys together, bromine and formic acid, because of the way the mechanism works, the concentration of formic acid doesn't affect what the rate is. It's only dependent on bromine. So, but what we're going to see is that we figure that out by using the experimental data. So when I give you a normal equation, and we're going to do one of these, but so if it's A plus B goes to C, I have to give you the concentration of A, concentration of B, rate. A, B, rate. And from that, we'll figure out. And the way you know that it's not going to be proportional or dependent on B, is that when you figure this out, if the concentration changes by some amount, say a factor of 2, and the rate doesn't change, that means it's independent of how much of that one's there, right? So, it ends up that, most of the time, the coefficients that these guys are going to be raised to are going to be integers. In almost all the examples we're going to use, it's either going to be 0, 1, or 2. There are examples where you can get half orders, and there are even examples of where it might be cubed, but almost everything we're going to look at is going to be either 0, which means it's independent of the concentration, 1, it's linearly dependent, or 2, it goes as the concentration squared. If it's anything other than that, when you start doing them, you might want to check your work, because there's probably a pretty good probability that maybe something wasn't quite done right. Because 0, 1, or 2 is going to be 98% of the time. And so just keep that in mind when you're working the problems. It better come out to probably be 0, 1, or 2. So, if I hadn't said this already, K is called the rate constant. And it's a constant, but it's a constant for a given temperature. K changes with temperature. So it has to be, I have to give you a temperature where this is all taking place. And as I said, later on we're going to see where if we know K at a temperature and we know the activation energy, we can figure out what K is at other temperatures. Okay. Okay, yes ma'am.
So, by first order, do you mean that K has to be equal to 1?
No. K can be anything. So and actually we'll solve for K right now. So K, in this case, we just pick a rate and a concentration, and we get K. And K would be the same then at that temperature. When I say it's first order, it just means that it varies with bromine to the first power. And what that kind of means is, that it's a unimolecular reaction. One bromine is not interacting with another bromine. Or, and I use this one. Radioactive decay is a great example of a first order reaction, because if I have 100 atoms of uranium-235, this uranium-235 atom doesn't have any effect on this one. It's going to decay at a certain rate based on itself. When I go, if it ends up that the coefficient here is 2, that means those guys are talking to each other somehow. It may be that one bromine atom or molecule has to run into another one in order for them to split it or make bromine 3 or something like that. So first order just means that it's raised to the first power and that it's going to be what we call a unimolecular reaction. Okay? All right. So then this is how we get K, though, is that once we know the rate and we know a concentration, we've got this simple little equation. We just plug them in and we get K. K is going to, for this reaction, then K is always going to be 3.49 times 10 to the minus 3 per second, as long as we're at that temperature. Now, the other thing to keep up with is when you look at this, the units on K in this particular case come out to be per second. It's per second because rate is always going to be in molarity per second. For a first order reaction, it's bromine concentration to the first power, so it's in molarity. Molarity per second over molarity comes out to second to the minus 1. If it's a second order reaction, the units are going to be different. And the units on K are always going to be just to make them work out. If you try to physically think about what those units on K mean, boy, it's hard. Because it's hard to sort of rationalize or come into your mind. Why is it seconds to the minus 1 when it's a first order? And then the other one's going to be molarity squared, so it's going to be molarity to the minus 1, second to the minus 1. I'm not very good at thinking about what molarity to the minus 1 means. But the units on K, so always make sure when you get done, if I ask you to solve for K, make sure the units are right. If I give you K, look at the units, because that's going to tell you what order the reaction has to be. So you already get a hint if it's going to be first or second order if I give you K, because the units on K tell you exactly what the order is going to be without figuring anything else out. So make sure you pay attention to the units on K is the point of the story. But so, overall, we say it's first order. That just means that it only counts for concentration of bromine. Formic acid doesn't matter. And then once we get what order it is, we solve for K just using one set of the data. Okay. So, just as another example, and again, these are sort of nit details a little bit, but to your point, when we look at what things could we measure, we gave the example, and in this one, we have hydrogen peroxide decomposing to water. So this is in solution. Decomposes to water, to get oxygen gas. And if you've ever, taken your hydrogen peroxide bottle, when you open it up, and that's because the oxygen decomposes, a little bit of oxygen is built up, and you've got some pressure of oxygen. It ends up, if I can measure that pressure of oxygen, you know, I can get what the rate is, or I can get how much of it's been formed, because, you know, if we know from this, the change in concentration of O2, because it's building up, you know, divided by the time, that would give us the rate. Concentration of O2, you might say, well, gosh, how am I going to measure the concentration of O2? Well, if you remember, you know, this is one of those other things. You know, if you don't remember anything else from freshman chemistry, you ought to understand what the ideal gas law is. You know, does everybody, I mean, ideal gas law is what? PV equals nRT. What's one of the main things we need to remember? You know, I'll always give you R. You know, that's okay. We need to know that N is the number of moles, B is the pressure, V is the volume, T is the temperature, and it's the temperature in absolute, right? So it's in Kelvin. So I'll give you a hint. You know, I've taught this class, I think this will be the 5th year, 4th, I don't remember. Every year on the final, I'm going to have a question on there, and it's going to say, gosh, during the summer, I measured the pressure in my tires, and it was 32 psi. And we always have the exam 15th or 16th of December. That morning, it's going to be like 40 degrees Fahrenheit. So I'm going to say, okay, if your pressure was 30 psi when it was 105 degrees outside, what was your pressure this morning? I would say at least half of you will use Fahrenheit instead of Kelvin, and half of you are going to tell me that the pressure in your tires that morning was 1 psi. You know, and if you all drove in on 1 psi in your tires, you probably had to buy new tires. So, you know, and every year I tell you guys this at the beginning of the semester. You know, you really need to remember PV equals nRT. There really is going to be a problem on the final, and every year half of you will put down 1 psi. So, you know, make sure you think about that when it comes down to the final, because that problem will be on the final. You know, and if you can't get that one, oh man, that's really bad. So, if you don't remember anything else, PV equals nRT, but T has to be an absolute temperature, right? So, keep that in mind. But so, you know, after my spiel, so if PV equals nRT, we need to know the concentration of oxygen. So what is concentration of oxygen? It's just moles per liter, right? Well, N over V is just number of moles per volume, or moles per liter. So we can get the oxygen concentration just by measuring the pressure. If I know the temperature, so the pressure divided by RT is just equal to N over V. So if I measure the oxygen pressure, I know how many moles of oxygen, I know what the concentration of the oxygen is, I can actually get then, you know, from the ideal gas law, what this rate is, without having to specifically measure or knowing how to measure oxygen molecules. All I need to do is be able to measure the pressure of the oxygen. And from that I can get the concentration of oxygen, from that I can get back to the rate. Okay? But, you know, and it'll even be on the final, you know, it'll be on the list of equations. I'll give you PV equals nRT, but boy, that is one you probably ought to remember. It'd be embarrassing if you get out of freshman chemistry and don't know PV equals nRT. Okay, so, you know, we've been through this, you know, we said, okay, we're going to measure reactions, you know, this is, and we've already talked about this, the general rate is just, you know, 1 over this coefficient, change in concentration of A over time, B over time, C over time, all this. You know, so, you know, this is the general expression. You know, if I give you an equation, you can always write this general expression down, and it will always be right. You know, I mean, because it has to be by definition. That's the definition of rate. Problem is it's hard to use, right? Because it's hard for me to be able to measure, you know, on a regular basis what the change in concentration is. So, you know, while this is the general expression, and it's the one you're always going to see, in reality it's not very useful. So, you know, as we go through this, you know, we write this general expression, but what we really want to get to, you know, besides this, which, you know, we write all these guys down, we really want to get to that rate equation that we just showed for that one example. The rate equals a rate constant times the concentrations, but you know, the problem with that is that we have to have some experimental data. I mean, we can write this equation down, or this equation down, with no experimental data, right? I mean, all I got to have is the equation. If I have the reaction, I can write this down, and it's perfectly okay. If I really want to have something useful, I'm going to have experimental data, because if you remember, the rate equals the rate constant times the concentrations raised to that power. From this, I can't get the power, or I can't take that coefficient. And you really need to be careful, because, you know, there's a difference between putting the coefficient in front and just saying the rate in terms of the change in concentration versus time, versus the rate equals the rate constant times the concentration. So a lot of times the tendency is, and you know, the way you know, if you're not thinking and you get confused or you get rushed, you're going to say, well, gosh, the coefficient here is 1, so it's going to be rate equal k to, you know, the concentration to the first power. You can't tell what the power has to be from this equation. We have to use the experimental data to get there. So how are we going to do that? So in the end, this is what we want. So, you know, what's going to be useful then is the rate law. And the rate law is, you know, if we have that same reaction. So we just wrote down that reaction, you know, rate equals, you know, delta A over delta T, delta B over delta T, you know, plus delta C, all that. But what we really want is the rate equals a rate constant times the concentration of A to some power x times the concentration of B to some power y. And the reason that that's important is because, you know, if I'm really trying to design a process and I want that process to work at a certain, you know, rate or a certain speed, and I want to be able to make so much product per hour, you know, I'm going to be taking the products away. What I'm interested in is how much am I going to have to feed into it. So how much reactants do I need, or what concentration do the reactants need to be to generate this amount of product? And the way I'm going to tell that is by being able to write this expression and solve for it. And so, as we've said, K is the rate constant, X is the order with respect to A, Y is with the B, and at the beginning we don't know what X and Y have to be. From this, we can't tell what X and Y has to be. So, you know, again, you know, sort of the sort of tendency is, well, gosh, X has to be equal to A, Y has to be equal to B. No, I don't know that until I actually look at it experimentally. And so in this case, you know, if we looked at bromine plus formic acid going to bromide, hydrogen, CO2, the rate expression that we want to write is rate equals K times Br2 to some power X times formic acid to Y. A term that we use in you know, overall is that we give the overall order of the reaction is just X plus Y. So if X plus Y equals 1, we call it a first order reaction. X plus Y equals 2, we call it a second order reaction, and so forth. So it's the sum of those coefficients is what's going to define the overall reaction order for the reaction. So, you know, this is the one that we've been looking at, bromine plus formic acid. This would be the overall rate. How do we actually use experimental data then to find X and Y? Okay. So, as another example, you know, this is a particular reaction. F2 plus 2ClO2 goes to 2FClO2. So, how are we going to be able to determine, you know, what this rate equation is? And so, you know, we can write down the general form of the rate equation by looking at the reaction. It's K equals concentration of F2 to the X power times the concentration of ClO2 to the Y power. Okay? So now the trick is we need to be able to find out what X and Y are. In order to do that, I have to give you some data. So if we go back and look now, let's see what's... Yeah, okay, we'll do it this way. Okay, so all that other stuff in there. So if I want to figure out what X and Y are, I want to be a little bit clever about how I look at the data. So, you know, I've given you 3 sets, you know, from 3 different experiments. If I want to find how the reaction varies with respect to the fluorine concentration, what I want to do is find experiments where the ClO2 concentration doesn't change. Because if it doesn't change, I can cancel it out, right? So, you know, in order to figure out how the rate varies with the concentration of fluorine, I just look at my data and I say, okay, if I use experiment 1 and experiment 3, the ClO2 concentration is the same, so it cancels out. So, you know, I don't have to worry about what Y is. You know, the rate constant's a constant because I haven't changed temperature. So all I have to do is look at the fluorine concentration from experiment 3 divided by the fluorine concentration from experiment 1. You know, it's 0.2 divided by 0.1, so it varies by 2. If I look at the rate for number 3 is 2.4 times 10 to the minus 3. The rate for number 1 is 1.2. So the rate changes by a factor of 2. So I have 2 for the concentration. 2 to what power equals 2 for the rate. So, you know, if I think about this, the way I want to do it is that I have a change in concentration of F2 as 2. 2 to what power X equals 2. So what would X have to be? 1, right? So 2 to the first power equals 2. So we know from this that the reaction must be first order in F2, so X must be equal to 1. So now we got X, now we want to look for how do we solve for Y. Same idea. Let's find a set of experiments where the fluorine concentration doesn't change, but where we get a change in the ClO2 concentration. So if we look at reaction 1 and 2, in this case, F2 is constant, so it doesn't change. The ClO2 concentration changes by a factor of 4. The rate changes by a factor of 4. So we have 4 raised to some power equals 4. So if we do just like we did before, and check that out, 4 to the y power equals 4, y must be equal to 1. So the reaction must also be first order in ClO2, or y equals 1. Put all of it together, and so then the rate overall is just the rate constant times the concentration of F2 times the concentration of ClO2. So everybody got that? You can guarantee there'll be a question like that on the test. Yes, sir? It's fine. Yeah, I mean, you can do them either way you want, as long as you just want to make sure that you put, for the concentrations, if you're going to put 1 over 2 for the rate, you put 1 over 2 for the concentrations. If you're going to do 2 over 1, just do them both the same. Okay, so just be consistent when you put the concentrations in the rate. That's all you have to worry about. So, everybody knows that? Everybody sees this? Like I said, I can guarantee you there'll be one like this on the test. So if you don't see it, speak up.
I got a question.
Good.
So that reaction of the first order and ClO2 and fluoride, and it's 2 overall.
So it's second order overall. That's right. So overall would be x plus y. In this case, 1 plus 1, 2. So if I ask you what the overall reaction rate is, it would be second order. And so what that means, from a mechanistic standpoint is that, I have to have a fluorine molecule and it's interacting with that ClO2 molecule. They're coming together somehow for this reaction to happen. Okay? All right. Yes?
So because the equation is 2ClO2, should there be a 1/2?
No. Because, and that's what we don't want to get confused, and that's why it's a great question. We use the 1/2 when we're describing the rate when it's the concentration divided by the time, right? Because, then we're trying to compare how would it change relative to F2, how would it change relative to FClO2. When, we're just looking at the rate equation, all we're interested in is what's the concentration and what's the power raised to. Okay? So don't, that is a very easy confusion to have. So make sure you don't, the numbers here have nothing to do with what we end up down here. Okay? All right. So then the next step is, oops, no, I thought I did that, but I didn't. Okay, but yeah, I should have. My bad. Typically what you're going to get on a problem like this is the problem may be as easy as, or the question would be as easy as, I'll give you this set of data, and I'll say what's K. So, don't be lulled into that, okay, gosh, well, K is just the rate divided by, the concentration of F2 and ClO2. First thing you have to do is figure out what the coefficients are for F2 and ClO2. I mean, again, a large fraction of us are going to, I would give you this set of data and say, what's K? First thing you're going to do, gosh, you're just going to plug in this, and you're going to come up with K, and you can be pretty sure on the test, I'm probably not going to make them both 1, so that you get the right answer just by not knowing how to do it. So first thing you have to do is find the coefficients. Once you get the coefficients, then you solve for K. And even though the question is just solve for K, you can't get K until you know what the coefficients are. Okay? So in this one, and I didn't actually, I left that slide out. Go ahead and you'd solve for K just by pick one of the equations. My first one, so it'd be 0.1 times 0.1. You would take the rate divided by that, you get K. And what would the units on K be this time? Anybody know? Correct. So it'd be molarity to the -1, seconds to the -1. Okay? All right. Another example. And this is one just to, so you don't fall into the trap of, it's okay, gosh, what's K? Given, this set of data. Coefficients may not always be 1. So how do we do one where the coefficients aren't 1? If we look at this equation, how are we doing on time? So in this case, we have, A plus A sub A, BB goes to C, C, D, D. So the rate is the rate constant times A to the X, B to the Y. So we go through exactly the same way we did it on the last one. Let's pick an equation, or pick a set of experiments where B is constant. So B is constant here. Here, the concentration of A, when the concentration doubles, the rate doubles. So what's X? 1, right? Okay, good. So X is 1. When we go through that, okay, that all looks in here. To your question, Doesn't matter, as long as you do them the same, okay? So okay, first order in X. Now, we need to find Y. So let's pick the next two. So we pick experiment 1 and experiment 3, because now A is constant, so we don't have to worry about it. You know, B doubles. It goes from 0.15 to 0.3. The rate goes from 2.1 times 10 to the minus 4 to 8.4 times 10 to the minus 4. So the concentration goes up by 2, rate goes up by 4. What must Y be? 2, right? Because, you know, when the concentration has to be squared in order for the rate to go up by a factor of 4. So what would happen then, so concentration's 2, rate's 4, must be second order in Y. So overall, the rate's going to be K times A times the concentration of B squared. Well, and if I plug those guys in, and again, you know, probably the question would be, what's K for this set of reactions? So first off, you need to figure out, yea, verily, that it's, you know, A to the first power, B to the second power. You know, so I pick one experiment, 2.1 times 10 to the minus 4, 0.15 squared, 0.1, work all this out, K comes out to B, and in this case, it's 9.3 molarity to the minus 2, seconds to the minus 1, because what's the overall order for this reaction? Third, right? This would be a third order reaction because X plus Y equals 3 on this one. So, again, you know,